clicking record. Some logistics. The homework's due at the beginning of class on Tuesday. I'm missing Tuesday because I'll be in Santa Barbara for a choral meeting, but I'll be available online on Monday somewhat if people have questions. Same with the last homework. I'm a little skeptical that everybody will be able to do it the last night without assistance, but I mean, it's possible that Slack will fill that gap. But again, I'm kind of encouraging people to get started ahead of time, and we can start talking about stuff during the last day. And then in terms of projects, I started talking. Caitlin and I have talked. I'm assuming because everybody's grad students that people probably have their own projects in mind already. But just in case anybody doesn't, I was talking with Chelsea Wood, who's here at SAPS, and she has a really interesting data set looking at schisto, where people, basically, my understanding is that schisto, is a disease that impacts a lot of humans in developing countries, that like a lot of diseases, it has sort of like multiple stages in its life history. And in fact, when they start doing these very effective human treatments and sweeping from upstream downstream, there's still these reservoirs of schisto in snails. And so now that, the WHO and others are realizing that to deal with schisto, they need to not just deal with the human side, but the kind of ecological side. So my understanding is that she has a data set where they go out to, 10 villages and 20 access points among those villages, and then sample quadrats to look at the spatial scale of variation and also what covariates are associated with high levels of schisto. So like what pH, what temperature, what vegetation, and so forth. So it's a neat spatial data set. She's looking for people that are interested. And so maybe a show of hands whether people have a data set already in mind, kind of in a preliminary way, or. Okay, yeah, so I was telling her it's a little unlikely that anybody would take the bait on that. But if anybody's curious, I still do think it'd be a cool project. Okay. And Jay, no Jay. Yeah. Okay, so I should have redone this for a small. So today we're gonna start talking about the simplest population model, which essentially takes a Kalman filter and builds in a little bit of extra structure and then can be interpreted in terms that we're used to thinking about as ecologists in terms of density dependence. So what, anybody want to define density dependence?
Mathematically or just sort of generally?
Either one.
Generally, when you have a super high density of animals, sometimes they have interactions, and so that sort of caps how much larger the population can grow.
Totally. So there's something about carrying capacity. There's something about interactions that causes a cap on population size to emerge. How about, mathematically, how do we define density dependence?
Some logistic relationship or something.
Yeah, well, oftentimes we have a specific model, but I don't know if people have read Strong or Chesson or other ecologists that try to define what's sort of the bare minimum to say that a model has density dependence. If you get a model and you've never seen it before, how do you know if there's density dependence?
What do you mean, you get a model?
If somebody just hands you a model and asks you, is there density dependence in this model or not?
You have some thing divided by some, you have some division sign in there, I guess. Look at that.
The rate of change of the population is related to the size of the population.
Yeah, so typically the way people define it is something like the per capita productivity changes as a function of population size. So that sort of the per capita, involves a division, and it has something to do with, a function that depends on population size. And yeah, so we're gonna take this directed walk model, directed random walk model that had 3 parameters, and we're gonna change it to make it have density dependence. Anybody, I mean, I presented this a lot around SAF, so, and I mean, other people use this a lot, like the Eric Ward and Mark Sherrill and Eli Holmes talk about Gompertz density dependence a lot. And apparently Gompertz also has a well-known growth, I mean, he has a growth curve, but I understand he also has some role in public health stuff from last time, so I think that this is a different meaning of a Gompertz model than the public health Gompertz model people are used to doing. Anybody have any intuition about how could you insert density dependence into this model?
Alpha varies as some proportion of x of t.
Totally. So one way to do this would be to put some dependence in here. And if you do the algebra, you can also say this is normal with a 0 mean and put the alpha in this equation. And so one way would be to think about having alpha be a function of x. And that's essentially what we end up doing. Here's a data set that I simulated that I think looked a lot like the last lab. And again, I mean, if we just get a data set like this, how would we, any ideas about how we would say whether it has, whether it's likely to have density dependence or not? I mean, eyeballing it, maybe it looks like it kind of goes up and then hits a carrying capacity. So kind of intuitively, maybe we think it has density dependence, but how would we go about sort of making a statement like this has density dependence, no it doesn't, or how certain are we about that?
Make 2 models, one with density dependence, one without, and then do some sort of model comparison.
Sure, and that's the sort of like parametric approach. I mean, there's people who also do like fits, try to make a some non-parametric. Well, I guess you could do the same thing. You could fit a non-parametric model without density dependence in a non-parametric. We're going to go ahead and because we're doing in probability modeling land, we're going to go ahead and make sort of parametric probability models for each of those and compare them. Yeah, and so essentially the questions. I mean, we've talked about. Is there evidence of density dependence? What's the expected equilibrium or carrying capacity? Other stuff we might care about is like the stationary distribution of abundance. So like, given that it hits carrying capacity, if you run an equilibrium, what's the variance around that carrying capacity? Or ecologists, a lot of times want to answer a question: how stable is the model? We can come back to stability if people are interested. So the Gompertz model, like Nat was saying, is essentially taking, well, if you think about it in log space, so if you take the logs on that first line, it's essentially saying that the mean of epsilon, so this could be the mean of epsilon from, alpha minus beta times log density is the equivalent of alpha previously, and we're just putting it up into the first line. Suddenly alpha becomes a function of, log density. Anybody want to walk through the algebra of that in more detail? Or? So, and you guys must have studied this in Idaho a lot, I suppose, because Brian Dennis was there, or did he?
I think he went over it in one of his classes, yeah.
Yeah, but he wasn't, that's it, I mean, I don't know how interested he was in this stuff.
Yeah, he mentioned it, I think, in like statistical ecology or.
Okay. Well, if you plot out biomass in year, I should learn that this thing never goes to the bottom. If you plot out biomass in year t against biomass in year t plus 1 against biomass in year t, this is what we often, well, technically we call surplus production typically biomass in year t plus 1 minus biomass in year t against biomass in year t. But that's the same as this plot and looking at this curve relative to the dashed one-to-one line. And so the difference between this function and the one-to-one line is what we in fisheries call surplus production, or ecologists might call it population growth rate.
So A over B is just carrying capacity then, right?
Exactly. And how do you know that? Or,
Well, I'm thinking if like exp 0 is 1, so.
Sure.
Yeah.
Yeah, you can get that. You can derive it from a power series expansion, or you can do kind of like do moment and kind of start plugging stuff in. I mean, it's simple enough that you can kind of plug stuff in and just confirm it works. Yeah, or what this is saying is that the log biomass in year t given biomass in year t minus in year t plus 1 over log biomass in year t is linear. So there's this linear increase in in this, however you want to interpret this. Any intuition about why this model wouldn't make sense? Any guesses at what the pros and cons are of this model so far based on what we? Yeah, feel free to chime in online too if anybody is interested. Yeah.
One con seems like it would start off with the highest growth at the beginning, when I feel like if you start with a very small population, it doesn't really make sense to have a huge population growth.
Yeah. Well, right. In fact, so if you in the limit as the log density goes to negative infinity, or as density goes to 0, the per capita growth rate goes to infinity. So if you start the population off at 0, the next year it's expected to go to, well, we can see this. Maybe I'll get a few more slides and show, I'll skip forward a little bit. This is if you log scale that first line. Take the log of the first line. And so if this goes to negative infinity, okay, so I'm like, you're fine. Yeah, well, let's see. So now I should have looked at this again. So yeah, one problem is that as the log density gets really low, the per capita growth rate goes to infinity. So it doesn't really make sense outside of, it doesn't really make sense at the extremes. That's what you started out by saying. Are there any benefits that people can see to this model offhand?
Can you clarify biologically what alpha and beta would represent?
Sure, that's a good start point. So going back a couple slides again, so here's the curves. I mean, if I get a new model, the first things I do are always just plot it and then start trying to interpret what the parameters are. And let's see, you can see something about how this beta is the strength of density dependence. And that makes sense because it's this term that's multiplied by density to make, growth rate some function of current density. You can see that if, let's see, you can see that if you plug in alpha over beta as the carrying capacity, so if this is a carrying capacity, this ends up being just alpha. Sorry, I should use the pointer. So if this density goes to carrying capacity, which is alpha over beta, and we can come back to how to derive that later, then this product is alpha. So this term is 0, so this equals 1, so that it's density in time t plus 1 equals density in time t, which is the definition of carrying capacity. But if if density gets really small, let's see. Here's where I'm mixing myself up. Well, essentially, if you look at the plot here, you can see that negative beta is going to be the rate controlling the slope of this curve, and alpha is going to be the slope, the basic, well.
Inflection point where it,
Yeah, I'm sorry. Yeah, exactly. So I should have looked at the function a little bit more. Instead, I spent this morning kind of coming up with the exercise. So beta is going to be controlling the slope, and alpha is going to control essentially the level of the carrying capacity. And that makes sense. That's one way to think about it. It makes sense that this model has sort of two moments, one of which is the slope of this curve, and the other one being something controlling its height. Let's see, the other things in the model, epsilon sub t is the what I've been calling the process error. So what are other things that might contribute to process error? We, like Caitlin, you and I had some back and forth about process error previously, where my memory is that we landed on kind of the claim that process error is sort of the other stuff that we're not modeling. It's not exactly error. It's error with respect to the model, or if you're thinking biologically, it's just all the other stuff that we're not bothering with. And then b sub t, the log b sub t is the index that we're fitting the model to. Let's see. So how would this end up reverting to a random walk model, a directed random walk model like we were looking at before? So I'll just claim that this model, includes the directed random walk model we were looking at already as a nested submodel.
When beta goes to 0 and it's not.
Yeah, exactly. So if beta goes to 0, then there's essentially no density dependence, and the model can follow a random walk. And if that's the case, what's the interpretation of alpha if beta equals 0?
population growth.
Yeah, so alpha is the same as the alpha we had in the previous model, where it's sort of saying, is the model trending upward or downward over time? Let's see, and what happens? Maybe I'll keep going a couple slides, but Caitlin did that. Now I'm missing anything that?
That was helpful.
Okay.
Thank you. Yeah.
Okay, so the way people write this out, well, it's called the Gompertz model, and I think Gompertz lived in the late 19th century, and so this is a very old model. The way people set this up is they define 1 minus beta as rho, and if you plug rho in up here, it looks identical to the directed random walk model, except suddenly we've got this autoregressive term. So the reason that this model has some history and why it continues to be used is it's identical. It's the simplest biological model that's identical to a simple time series model, linear time series model. So technically this model is linear in log density. And because it's linear in log density, people like Gompertz could, draw some points on log density of rabbits or whatever on a curve, fit a line by eye, and then start interpreting, read off that line to look at what the carrying capacity is, what's the degree of density is, and so on. Yeah. Okay, so if we fit this, these data that we started with, I hope these are the same data. No, I forgot to update the slide again, but if we fit a data set with the Gompertz model using essentially the same code, and we'll see it in a second, that we did on Tuesday, we can get back these sort of predictions of this unobserved state using a state space model. And if we compare that with the true value, we get, again, we get sort of a plausible fit between our estimates and estimates of uncertainty relative to the true model. Okay, so let's say that, this notation sort of sucks. But the carrying capacity, as Grant already said, is alpha over beta. And I'll just propose that the stationary variance is the variance of the process errors divided by beta as well. Can anybody, how would we, so Grant, you, for instance, you solved this, if I understand it right, by some kind of intuition that then you can confirm by plugging it into the equation. And my response was that we could solve this by doing some, power series formula. Anybody want to elaborate what that means? Or any other intuition about other ways we would solve for what that expectation is? I know that not everybody will have had any experience trying to work out what the stationary distribution of a stochastic, process is, or what a stochastic model is. But what are the different ways that you might solve that if that was a problem you had to solve for a paper?
Well, if it's stationary, we want to go back to our system of equations and we say dt plus 1 equals dt. Solve for that d.
Yeah, so exactly. So that would be like if it's I guess I'm used to doing that in terms of like a deterministic system. Not sure if that works so well in a stochastic system, but maybe it does.
Well, you could solve it for the expectation of dt plus 1.
Totally, right, exactly. So, so you could solve for the expectation of dt plus 1, so you could take this first line and say the expected value is equal to, because I'm defining this as normally distributed with a mean of 0, so this epsilon drops out. And solve for dt plus 1 equals dt.
Why? Why does the epsilon go?
Well, if you're taking the expectation of the right-hand side, the expected value of the right-hand side, the expected value of an equation is, if it's additive, is just the expected value of each additive piece. the expectation of a constant is that constant, and the expectation of this epsilon is 0 because it's a normal distribution of mean 0. I really have to remember to bring my notepads that I can take, do algebra that people online can see. Let's see, and so I'm always scared about doing algebra on the fly like this. But if we do that expectation, well, anyway. Yeah, and then another way to do it is, another way you can always do this is just Monte Carlo. I mean, that's sort of what I guess people, I think, that's my cartoon of what we often do in fisheries a lot is if we don't know the answer analytically, we, simulate it, which I think is totally respectable. So we could always just simulate this model, simulate it out to time infinity and take the, take a burn-in of 100,000 years and take the mean and the standard deviation. Because it's a simple model, it'd be pretty easy to just start kind of exploring by hand and work out what that would be.
What do you mean by doing it by the power?
Yeah, a power series. So my claim is that, it's just an it's an autoregressive model, and so the variance of the stationary distribution will be the accumulation of the variance for all of the previous lags. And so, if you do that, you end up, where epsilon the year before has been, that process error has been decreased by rho, by a factor of, it's multiplied by 1 over rho. 2 years ago it was multiplied by 1 over rho squared, and so on, and that's a conversion series, as long as rho is between -1 and 1. So you can, so Brandon online asked why I don't consider rho equals -1, or did you say beta? I guess I can see your notes. It only popped up for a second before it disappeared. Yeah, exactly. So any reason why I don't consider rho equals -1? And thanks for asking. So if rho equals -1, then that means that beta equals 2, I guess. Okay, so if rho equals -1 in this equation, well, what happens if beta is greater than 1? Okay, let's just start with what equals if beta equals 1.
Beta equals 1, there's no density dependence.
No density dependence. How about if beta equals, if beta equals, I'm sorry about this. I really should have spent more time looking at this equation so that I wouldn't get mixed up when I'm converting between rhos and betas. Okay, so if beta equals 0 and rho equals 1, it means it's a random walk. That makes sense. And if beta equals 1, then it just means it's fluctuating independently around years. So there's, so it will always revert to its carrying capacity the next year, regardless of what its value is in a given year. But if beta is greater than 1, okay, so if beta equals 1, it always reverts to its carrying capacity every year. If beta is greater than 1, what happens in this model? Where I'm trying to get to.
Would it have sort of a positive density dependence, or it would increase as density increases?
So why don't we just simulate this a little bit? So if we've got log biomass equals 10,000 years of made up data, and log biomass in year 1 starts out at 0, and we've got rho equals, we've got beta equals 1.1, or let's just start out at 2. So, let's start out at 1.5. And so if beta equals 1.5, rho equals 1 minus beta, so rho would equal negative 0.5. And that's the kind of halfway point, that's sort of going along the direction of what Brandon is asking about. So from this equation, I'll say alpha equals 1. And I'll just drop out I'll just say that the process errors get really small so that we can explore what's the properties of this model. I never actually code this way without actually writing a script, so hopefully this works. And if anybody sees what it's doing, feel free to chime in. So is this the model correctly? So there's too many years to really see it very well. So I'll just cut it down to 25 years just to show it. So this is what we get for the deterministic part of the model. The deterministic part of the model, if beta is greater than 1, so that rho is less than 0. And what's happening? I know it's kind of bright.
Sort of wildly fluctuates around what looks like carrying capacity.
Yeah, exactly. So it's just doing this sort of convergent oscillation to the carrying capacity. And for people that have worked with an autoregressive model, they would have some, intuition that if you've got a rho, if the first order autoregression is negative, you've got this sort of oscillatory thing going on. So what happens as beta gets closer to 2? So if, let's say we do beta equals 1.9. Any hypotheses about what will happen here?
Takes longer to converge.
Yeah.
Capacity.
So the two hypotheses, one is that it gets more chaotic, and one is that it takes longer to converge, and so and maybe this is what you mean by chaotic. There's sort of another kind of way of talking about chaotic dynamics. That and this isn't chaotic in that other sense, but it's oscillatory, oscillating. The oscillations are taking longer to damp. And so as beta goes to 2, let's just put in 1.999. As beta goes to 2, it just doesn't dampen at all. And that makes sense. So if beta equals 2, from our formula that we didn't really derive, we have that. I'm sorry, this should be 1 minus. I'm going to double check those formulas, but sometime after we start doing the exercise. But what we showed here is that this rho equals 1 minus beta, rho in a first order autoregressive model. And so as beta goes to 2, rho goes to -1, and if you have a -1 in a first order autoregressive model, it'll just fluctuate, without ever achieving the carrying capacity of the deterministic part. And so that means that there's no equilibrium anymore. So that we can only do the power series expansion of this model if it's convergent, which means that in that case, rho has to be between -1 and 1. I'm sorry. So we'll see this model again when it comes up in the spatial model in week 5, or kind of a variant of it. And in that case, we'll work through those sort of properties a little bit more. Okay, well, the point of this was to introduce the Gulfport's model, which is the simplest sort of model that takes our directed random walk. It adds one additional parameter, and suddenly we have we end up with something that we can interpret as a biological model in which we've got surplus production, which is sort of the difference between the black line and the 1-to-1 line. So we get positive surplus production, but below the carrying capacity, and negative surplus production above it. And the claim is that we can use that model, we can fit it to a data set, and we can compare our results with and without that carrying density dependence, that fourth parameter, to determine whether there's some evidence of carrying capacity in a given data set or not. So is everybody on board with that? That basic message at least? Okay, so I'm going to change gears for a second and talk about the map argument in TMD for a second, and then the map argument is something we'll be using in the homework, I think. At least that's the simplest way to do the homework 2. And then we'll also use it later in this lab. So who's actually started the homework? Have people gotten? How far have people gotten?
TMD files.
Okay. Yeah.
That's where I'm at too.
Yeah. Well, that's no mean thing. Has anybody tried to start making the 4 different estimation models using the same CPP file?
I started trying, I haven't gotten it.
Yeah. Okay. So the hint that I gave was that the easiest way to do that is using this map input to TMD. And the map input, I didn't talk about it that much when I taught the class 2 years ago. The map input has 2 basic roles. So one of them is turning off a parameter, and that's what we're going to talk about today. And the other one is what we call mirroring a parameter, or making some set of parameters in your C++ file all have the same value. And so both of those features are ways of taking a single CPP file and making it do multiple things when you actually fit it. It's ways of imposing restrictions, either that some parameters are fixed at their starting value, or some of them are fixed to equal other parameters. And so to demonstrate this, I'll just go back to the linear mixed model that we were looking at in week 2. So we simulate some data. This is the simplest sort of linear mixed model design, where we've got 10 different sites, and each site we've sampled 10 times. Each site has some normal, all sites have a certain mean, x0, that represents the average density of something at that site. Every site has some deviation away from that mean that's, I'm calling here z, and then each sample has a normal measurement error. So it's a normal linear model. Or like in Gelman and Hill would call this like a random intercept model. So, the question would be, you know, what you might want to do, you know, if you're looking on the C++ side, you know, we've got the crazy gibberish at the top, we've got the reading in the data, reading in the parameters, and hopefully by now people kind of know to just skim to reading the actual block of working code. So there's the block of code that tells what's the probability of the data given the random effects and the fixed effects. And then there's a block of code saying the probability of the random effects. And just like is this too hard to read, people on site with the blue highlighting? It's kind of hard, isn't it?
Can we turn the lights off? That might be a
Yeah,
little bit.
that's a good idea. Is that?
That helps a little, yeah.
Okay, so you can see that this model is coded where Z, you know, the predictor, the linear, what I call linear predictor for data Y is the sum of the global intercept and then a site-specific deviation, Z, and the site-specific deviations are given a normal distribution that has a mean of 0. So, you know, you might want to fit this linear mixed model and compare the results with a model in which you eliminate a random effect structure. So it would, you know, just compare it with a linear model with no variation among sites, among groups. And so one way you can do that is to make a second C++ model and call it a linear model, cut out this block of code, you know, cut out this block of code, and I guess cut out Z and SDZ. And then you'd have to cut out other references to SDZ. And at this point, you've got a pretty different C++
There's
file.
one more in the report.
What's that?
There's one more in the report.
Okay, yeah. There we go. So yeah, I mean, so that only takes a few seconds, so it's really not impractical. The problem is that, you know, if you're doing a dissertation, you might eventually decide that you want to make some small change, and if you've got each of your models as a different C++ file, I mean, this is what I did in my master's. I had a bunch of JAX models that I coded up separately, and then I would make a small change, and then I'd have to make it into 25 models, and I'd never really make a typo in one of them, and then I'd have some results that didn't make sense. And so I think that you know, it's good for us to get in the habit of not, you know, of trying when we can to have a single working, you know, set of working code. So pretending that we've got, you know, this option called map that allows us to turn off parameters, how might we, on the C++ side, just looking at it, how else might we implement a linear model using this code?
You could turn off, or you could set log ZDZ or SDZ to 0, or to.
Well, so I think that there's definitely a way to do it along the lines of what you're saying. If you set this log SD0 to 0, then SD0, you know, SDZ equals 1, and
Yeah.
that's not the, but you could, so one way to do it, if you want, so the linear model with no group level variation is the limit as log SD0 goes to negative infinity. And so one way you can do this is not change the model at all, fix log SD0 at some tiny, you know, negative 20, and let the model run. And that would actually work, and we could show how that, we could see, you know.
Or you can set ZI to 0.
Yeah, so the way that's friendlier to your computer, I mean, of course, it's a funny, you know, the problem with defining a linear model as the limit of the mixed model where the group level variance goes to 0 is that you're forcing your computer to do all these integrals that you know that aren't doing anything. So it's kind of mean on your computer. And you know, the way that's friendlier to your computer is to say that every element of Z equals 0. And then turn off log SDZ and just not interpret its value at all. And so that's what I show on the C++ side, and the syntax for that looks like this. So previously, when we've called the make AB fun, we've called this function with an input data and an input parameters. And the new input here is map. So if we remove map and run this model, we just get oh yeah, because so there's one complication that we'll talk about here in a second. So if we want to do the way we've done this previously, we put, we compile it looking like this. And if we look at the log STZ and log ST0, well, in this particular replicate, log STZ is going away from what we know the true value is 1. But otherwise, the model seems to be working. I mean, the final gradients all look good. The standard errors look good. There's no warning about the Hessian not being positive definite. So the way we turn this, the way we reduce it down to a linear model is we input something into this tag list called map, and I'm just used to doing the syntax this way. You could instead write this a couple different ways, but the point is to end up with a tag list that looks like this, where there's multiple elements, of this tagged list, and each element is either is a factor that contains either NAs or integer values. And so, in this case, this is saying that you want to turn off the value of log ST0 so that it stays at the starting value, and you want to turn off every level of random effect Z. So if we compile that model, if we put map back in, if we put map back in and run it, and build the object R now is, instead of 3 parameters, which we had before, it's x0 and log ST0. It no longer has log STZ because that's been turned off. And we can run the model and get the same, the same results that we would get if we ran this linear model. So just to confirm that. That's funny. I don't know why that gives us slightly. I'll have to double check that later. Let's see. Well, there we go. I think I just reran the data, some block of code above and updated it. But so in this case, what we did is we turned off log STZ, we turned off Z, the random effect. We run, we recompile the model and we run it, and we get back the same result that we would get if we given that we expect it to behave like a linear model. So, any questions about how map is working in this instance?
So you want it to be a factor that is NA to turn it off. And then you said you could set all the, you wouldn't do this, but set all the Z's equal to each other, then presumably you'd have a factor
Totally.
1 for all of them, or if you wanted to set half equal, the other half equal,
Totally.
1 and 2 kind of thing.
Yeah, you could start doing, John premised this by saying you could do all sorts of wacky things. And as long as it has the right length, it'll compile. So in this case, this input to map is saying that we want to turn off the first random effect and the 6th, 7th, 8th, the 1st, 7th, 8th, 9th, and 10th random effects. We want to estimate 4 random effect values and the second and the fourth are the same. And then the third, fifth, and sixth have different unique values. And we could pass that to, and we'll, in this case, we'll turn back on log SDZ, hypothetically, and compile it. And because it's random, it's turning off those parameters, so it's hard to see. So I'll get rid of the random part. And as expected, we have 4 different elements of Z that we're estimating, corresponding to the 4 levels of that factor we pass it. The 4 non-NA levels of that factor we pass it.
And so by using the different numbers in there, you're indicating that, say, like, position 1 and 3 should be the same, as opposed to like giving it.
Yeah, I'm in the habit, I just am used to giving it numbers, technically, because it's coercing into a factor, it could be anything. So this could be second site, first site,
So,
third site.
Huh.
It could, because you're using this factor command to coerce it to a factor, so it ends up being the same thing.
Okay.
I don't mean to confuse the topic.
It's sort of like blocking an ADMD.
It's exactly,
Like you can set up blocks to say like these are the same and these should be different.
I spent so long since I used ADMB, I don't remember what the term blocking means in ADMB, but it's like mirroring in stock synthesis,
Okay.
which I think everybody has different terms for the same thing, but the concept is some parameters you want to turn off and leave in their starting value,
Mhm.
others of them you want to have take the same value.
Okay.
So in this case, let's turn off log SDZ again. There's one other point I want to make, and this is what Kristen was bringing up online on the issue tracker. So in this model, I'm not declaring anything as random, and so $$ represents all of the coefficients that are being estimated by the model. And I've got the coefficients are x0, log SD0, and 4 different values of z. But if I generate the report using $report, and I look at the report, I've still got 10 values of z in the report, and I've still got log, SDZ here. And so why is it that I've got different stuff in the report than the coefficients of the model when I in the object? So that's, I do love like those questions of like why, because you can answer them there's like a million causes for anything. So yeah, the best answer is why, because TMB is confusing. But, were you?
no, I'm also confused.
So the punchline is that when you $par is keeping track of the input parameters that your map argument is defining, but it's still tracking internally all of these parameters, and then these parameters are used to calculate the stuff that's being reported out in the report. And so if you turn off a parameter, all that's doing is it's saying it's fixed at its starting value, or it's fixed at some other way that map is working. So in this case, the starting value of parameters has log SDZ starting at 2, and so the e to the 2 is 7.389, and that's what's being reported out as SDZ. And so in the report, it's spitting out every calculation it's doing based on the parameters you're giving it. And the key is that some of these parameters, like this one is turned off, so it never changes the value of log SDZ.
But if you rerun your model starting from the best estimated parameters from the previous run,
Yeah.
then you have an input vector for z that's all zeros instead of with NA values. So wouldn't it?
So Say again? So how would you start it out with the best values for before?
Andre has a little piece of code that does it. I don't remember exactly, but I saw it once.
Okay, well, so one way to do that is,
He saves like the best parameter values from a run and then puts those back in.
There's
and
a-
restarts it.
there's a bunch of different ways to access stuff that's being used internally by TMB. So one of them is this par list function, and the par list, well, and some of it works for mixed effects models differently than fixed effects models, so, because this is a,
Actual value.
Yeah, can you just set map equals previous parameter estimates pretty much?
well, so that map is not the the parameters is the starting value parameters. Map is the thing that is a factor, it's a tag
Oh,
list
yeah,
of
yeah.
factors. But yeah, you could, if you generate your, I'll do this as a random model because
That makes
I'm kind of,
So even if you did keep your start value for the next time, you never change.
I've kind of made this to be a really confusing example in response to a previous question. So I'm just going back to the linear model case, just first of all, just to simplify what we're doing.
So if you don't want to make it a factor, you can just remove factor and set it to some numeric value.
Just give me a second here. I want to get back to linear models so that I'm not looking at this crazy example that I gave in response to John's question about mirroring.
So you never have to change the whole point is that you never have to change your CPP file, right? You can just do everything from R.
Yeah, typically, if you build kind of an umbrella model or an Uber model that contains all of the models you want as nested submodels, you can just use that as your CPP, and then you can generate those nested submodels by using the map argument. And so in the homework, we're going to look at, again, people, if the only way you know how to do it is to make 4 CPP files, then go ahead and I would really, again, the homework, I don't think anybody, as long as you turn in the homeworks on time and can accomplish the end of the homework, you will get a fine grade on the homeworks. So go ahead and do it with 4 CPPs with my blessing. But I encourage people to try to do it with 1 CPP and use the map argument to achieve the 4 different submodels that the homework has you do. So I think I've gotten back to the original linear model submodel. So in this case, map is defined where it's turning off log SC0, it's turning off the random effect, and so it ends up just with the same thing as a linear model. We can extract the we can extract the there's this object in $last par best is maybe one thing that you're thinking of that Andre uses to extract the best parameters. And that's defined in terms of the parameters like using the same format as obj_par. So it's defined using the same values that the user sees, the fixed effects. Alternatively,
Wait, why are those different?
because obj_par is the starting values,
Right,
and opt_par is the estimated MLE.
okay.
The other way you can access the best values is par hat equals, and it's probably gonna blow up due to TMB being confusing. So par hat, you can do obj and par list, obj par, and par hat, if in this case has the same structure as the parameters that you fed the CPP in the first place. So TMB sort of has 2 different ways you can think about the parameters. If you have a simple model with nothing going into map, the parameters you give it in this tagged list, it'll just divide up into random effects and fixed effects, and the fixed effects it gives in this vector. And it's pretty simple to think about how the parameters, the tagged list you give it, ends up with a set of parameters that the model cares about. But if you're using the map argument, it's doing all this stuff on the back end to transform the parameters, this tagged list of parameters you give it to start at, into the fixed effects that it's actually optimizing. And so, I don't know, you should just be aware that you can think about the parameters those two different ways. And if this code is helpful, maybe you'll remember that this option exists, Caitlin, for extracting the parameters in the form that it wants when you compile it, using this par list function that's buried in it. So this is a really long tangent, but maybe the 3 take-home messages is that map is a tagged list of factors. You can use it to fix parameters at their, fix parameters at their starting values or fix them to share the same value. And it can be confusing to think about. And so if you're using the map, you should be careful to double check that it's doing what you think it's doing. I think those are the 3.
So when you were doing the second example and you had like NA, first site, second site, that was saying that all of the ones that were tagged first site have to end up with the same value.
Exactly.
Second site.
Yeah. And you can do it as a character vector like that because it's contained within a function factor.
Okay.
And what factor does in R is it just coerces every unique value to have the same integer level on the back. Did I confuse things more by saying that?
No, that makes sense. So it's actually like NA, 1, 2.
Exactly. Those are identical. Yeah.
So how is the random command working in TMB? Because you assign it like which parameters are random.
Yeah, okay, so at the beginning of every lecture and lab, I typically have like a couple of review slides. And I probably should have had a review slide talking about this related topic of what's the inner optimizer and what's the outer optimizer. So these are sort of similar topics. So let's go back to what's the inner optimizer, what's the outer optimizer.
Inner is the Laplace approximation.
Yeah, and in more detail, what's it doing when it does the inner optimizer?
It's doing the Laplace approximation of the random effects to marginalize them out.
Yeah. Well, and it can only do that after it optimizes the joint log likelihood with respect to the random effects, given the value of fixed effects. And once it's optimized those random effects, it does the Laplace approximation.
Right.
And then it extracts that Laplace approximation and its gradients with respect to the fixed effects. And you use those to find the value of fixed effects that maximize this approximation of the log likelihood. So I don't know, well, okay, and then your question was about what is TMB doing when you declare something to be random?
Right, yeah. So is it sort of like map where when it sees, whatever that parameter is in the code, it recognizes it as a random variable?
Yeah, essentially, so the way I think TMB is working on the back end is that it applies map. So you've got this input of parameters that's a tag list. And it uses map to translate that input of parameters to a vector of parameters that's estimating. And that vector of coefficients that it's estimating. It transforms this tag list of parameters to a vector of coefficients that it's estimating. And to do so, it drops out elements of the map that are NA, and it also removes duplicates, for coefficients that you want to have the same value. So it's got this vector of coefficients that it wants to estimate, and then it applies the inputs in random, and it sorts out which of those coefficients are random effects and which of them are fixed effects. And if it's a random effect, if it has any random effects, it starts doing this inner optimizer step, where it optimizes the log likelihood with respect to those random effects, does the Laplace approximation, and outputs that, and its gradients with respect to fixed effects. So anything that's not listed as random is by default treated as a fixed effect. And TMB sometimes is squirrely because if you don't define anything as a random effect, it doesn't need to do the Laplace approximation. And so there's sort of, some functions work slightly differently if you have a model that's only fixed effects versus a model that has fixed and random effects. So in the user experience of TMB, I would say 9 out of 10 if you have times, if you have something weird happening in TMB and your model is all right, it's because of some squirreliness where you're doing like a fixed effects model, but that function is only built for a mixed effects model, or vice versa. That's kind of long explanation. You have any follow-up questions before we?
No, that helped a lot.
Okay.
Yeah.
We've got weeks to kind of keep coming back to this, so as long as we're making progress each week.
How sensitive are those to like starting values at all? Like,
You mean the random effects or the fixed effects or?
like both or either, because like, I think at one point I got a non-invertible Hessian issue, and I know like in the past that sometimes like
Yeah.
bad starting values, but that was definitely a model specification issue.
Yeah. So this gets into kind of more like, I mean, this gets, to know this stuff, you need to know more of the stats theory, which I don't know any way to learn except as a bunch of special cases personally, or being better at math than I am. But, like a normal model, I know that the joint log likelihood is quadratic, which means that the Hessian of the joint log likelihood for a given set of fixed effects is quadratic, which means that it'll always have, anywhere it starts, it'll get the same mode, both for the fixed effects and the random effects. So normal model guaranteed to be totally invariant starting points. I'm trying to think about other special cases that I actually know anything about. Like if you've got a Poisson log-linked glim, I think that it's guaranteed to be concave but not quadratic, but closer to quadratic, the closer you get to the MLE. And then in general, in nonlinear models, you can just end up with all sorts of crazy behavior. A lot of the models we'll deal with are essentially some form of generalized linear mixed model. And so the models we'll be looking at are generally concave, so they're generally guaranteed to not really matter where you start. Okay, so was this helpful in terms of talking about math? Okay, so let's go back to the original point of this. Maybe we take a 5-minute break, and then we'll come back and try this with a real world data set and do some changes to the code, the conference model code. So everybody come back by 10:15. Well, maybe I'll go ahead and get started. So the exercise today is to basically try to show how to modify the conference model to make it more relevant to the types of models we might talk about later in the class. And when I try to think about real world data sets, I always just come back to the data sets that I spent all this time sort of trying to figure out how to scrape effectively. So this is sort of, fish data. Fish data being this sort of package that harmonizes a bunch of data worldwide, and when in doubt, I usually just take data out of Eastern Bering Sea, which has sort of nice spatial dynamics. If you guys, Roy actually, after the class 2 years ago, suggested that I put in more public health examples, and I'd be happy to do that. But it would probably require knowing some data sets. So if if any of you is interested, feel free to put on the issue tracker, email me some way of just kind of porting it, sourcing it, IGME or GDB or whatever, data sets, that have spatial and temporal dimensions in some kind of sampling process, and I'd be happy to look at those and use them more. And then, so let's see, so the example I was gonna look at was trying to fit a population model to Alaska pollock. So as I think we mentioned, we looked at some spatial dynamics for Alaska pollock previously in the class. Just run it through so you can download fish data from GitHub using this command. Fish data, : download catch rates is just scraping off the Alaska Center website, the data for caddis, Calligramatis, or Alaska pollock, using its current designation. And local dir, if you supply local dir, it'll just save the data to your hard drive so that you don't have to burden the server with calling it too many extra times. So the data look like this, where, I guess did we use this for the homework actually? Did we use fish data, or we used a repository from, I think we used a static repository that I used for version control. So this is a somewhat more up-to-date version of the same data set that I scraped off the website, where, for instance, it has data up through 2017, where I bet the data set that we looked at for homework 1 stopped at 2015 or whatever it was. Okay, so the first thing I'm going to do is I'm going to generate an index of abundance in the kind of most naive way possible. So if people actually want to do this in the future, I don't recommend doing it this way. But if we had a simple random sampling design, and we assume that catch per unit effort, or CPUE, is proportional to local density of the species, then we could get an index of abundance, an index that's proportional to changes in biomass of the species by just taking the average of the catch rate averaged across all samples in a given year. And so that's what that t-apply statement is doing. Do people use apply t-apply stuff, or is that getting replaced in the tidyverse with some more confusing, greater than $ampersand thing?
I've mostly gone to tidyverse personally.
And so the tidyverse would do the same thing in some other way, maybe. I'm just wondering if people use t-apply statements, if that's like a way that I can show code that's readable to people. Yeah. Okay. So B sub t is just the index of abundance, where it's really hard to see that. This is where RStudio might be useful for teaching a class. But where abundance, I know from the assessment that it kind of went up in early years and then went down for a little while and then went back up, I don't know. And so, the same question is whether we can detect density dependence in this data set. And so if we just run it with the exact same model that we had before, we get this as output. So, so is this model converged, would people say, or not? So why would you say not, John?
Because I'm sorry, I was looking at this. No, I would say it is converged. I was looking at standard errors instead of final gradients.
Yeah, well, no, I don't know. Yeah, I actually don't have a good answer for this. Like that, based on the criteria I said before, all of the max gradients. Is this not zoomed in enough? for
Sorry,
people?
I have really terrible vision.
I'm-
If you could zoom in a little bit, that'd be awesome.
Yeah, no, sorry.
Thank you.
Yeah, of course, no. Let's see. So the point here is that, the criteria I said before is that the final gradient should be, close to zero, and the absolute value of the gradient should be less than 0.0001 or something. And that the Hessian should be positive definite, and the Hessian positive definite, all the standard errors should be and some number instead of NAs. And so both of those criteria are met by this model. But is there any kind of flag that the model might not be perfectly converged?
Huge standard error.
Yeah, so there's a crazy large standard error of 20,000 where the value is -11. And what's happening with that parameter? What is logged?
Well, is it have to do with like how they're not super identifiable, or?
Yeah, so in this case, log SDN, sigma m is going to -11, which means that, here, I'm gonna zoom out just a little bit so I can see that,
It's like 0.
yeah, it's less than 100,000. So, this sigma m is essentially going to 0. And so, the model is technically, quadratic around that MLE, and the gradients all look fine. But, anytime a parameter is hitting a bound, there's sort of reasons that you should be sort of skeptical about the model, so like standard errors stop working near a bound. And we see that with the standard error going to a crazy large number. And so, and if we plot out the results for that fit, we get this, where the data are in blue and the red lines and standard errors are in red. And why would we be skeptical of this? In fisheries at least, we just never think we can actually index the population size to precision of 0.000001. It just is fitting implausibly tight. The model isn't making sense. The model is also saying that we can perfectly reconstruct density of the species and have no error in our estimates of that. It doesn't make any sense.
Is there any biological constraint here? Like, I don't know pollen that well, but is it reasonable for it to go to 4.1 to 4.9 in 1 year?
Yeah, and we could probably make some inference about that too. And I don't want to, whether it is or is not probably depends on the availability of the stock, and there's a bunch of, stock assessment people would get into that question. But. Okay, so what I want to do, what I want to spend some time doing is adding in sampling variance. So instead of fitting just like a kind of vanilla Kalman filter or a vanilla Gompertz model, we're going to use the data to figure out what's a reasonable lower bound on the standard error of that index of abundance, and we're going to feed in that index of the standard error of the index and use that to improve our ability to discriminate between measurement error and process error. Does that make sense? So maybe another way of saying that, I'll put in another slide here, is we're gonna take this model and we're gonna make it have multiple sources of variation. So that suddenly the measurement error includes one component that's the standard error of our, estimate of abundance from our field sampling. And then we've got another component, sigma b, that is the additional variance in excess of the variance that we can measure from our field data. So, so why am I doing the sum of these two instead of the standard error plus sigma b without the squares? Any guesses, or why would people prefer to see standard error plus sigma b without the squares? You guys have any, I don't know if you know what stock synthesis does, like stock synthesis being the main stock assessment software that fisheries people use in this area. You guys know what stock synthesis does in terms of if you feed in the standard error of an index? If it does. So stock synthesis technically does the standard error. What stock synthesis does is, here I'll write it out. SS does, does that plus. So if you fit additional variance, stock synthesis does this.
CV plus.
What's that?
Well, that's the CV, right?
Yeah, but I guess I've been trying to convince Rick to stop doing it this way because, theoretically it makes sense to me that variances are, if they're independent, are additive. And so I want to interpret this as the variance of our index of abundance, our measurement from the field that has some variance that's due to the randomization of the sampling and measurement errors. And then there's some additional variance caused by biological processes that our model's ignoring, like movement of the fish in or out of the sampling area. And I typically think that those two sources of variation are independent, so I don't see any reason to think that the sampling variance is correlated with the biological things that would cause additional variance. And so if these are independent processes, then the variance should be additive instead of the standard deviations being additive. So that's why I'm doing it as the sum of the square of these two components. So taking a step back, I guess we already started talking about it. What does this term mean in this new modified model?
Standard error of the survey.
Yeah, so it's the standard error of the survey in a given year, and the claim is that we can estimate some of that standard error just from the variance in the sample of the data. And then this is the kind of additional variance outside of what we can obtain from the data. And so, but so we can calculate the standard error for the mean of a set of random variables by, the mean of a set, the mean of a bunch of random variables is just the sample mean of all of them, all of your observations. And the standard error of the estimate of the mean is just the variance between your samples. Well, the standard deviation of your samples divided by root n, if all of them are independent. So this is sort of derived from the central limit theorem. I'm not gonna, try to derive it any more than that. And so we can obtain, the claim is that we can obtain the standard error of the index abundance from the variance of each observation around the mean from that year. And so if we do that, I'm hoping people And then if you want to be fancy, you can convert that standard error to the variance of a log normal distribution, because of course we're actually doing the standard error for the log of an index, not the standard error for the index itself. So you can calculate the standard error for the index and then convert that to a log normal, the log normal variance. So people can do that or not, it's up to them. And what I would like you to do is take the Gompert CPP file and the R file, calculate that standard error of the index for every year, pass that into the CPP file, and modify the CPP file so that it uses that field sampling estimate of variance as essentially a lower bound on the precision on the variance of the observation process in the CPP file. So we'll spend maybe 15 minutes doing that. Does anybody have any questions before we get started? Maybe we take a second to say what do we need to change in the R file to do this?
You need to calculate a vector of those SDs or SD squareds.
Yeah, you need to make a new vector of the standard deviation or standard error, or whatever you want to call it, for the measurement process. And then you need to put that into the data, it needs to be passed to C++. And then on the CPP file side, what do you need to change?
You need to put in, just add that vector, parentheses.
Yeah, exactly. You have to put it in. You have to tell C++ to expect it.
Oh yeah.
Up here, and then you were saying.
Add it in the likelihood.
Yeah, just put it in here for the likelihood of the observation process. So we'll spend 15 minutes doing that. We'll come back at 11 or 10:50. For folks off-site, if anybody does this and wants to present it back to the class, maybe just text me in the chat bar and I could make you the presenter. But no worries if nobody volunteers. Zoom recording. I'm still sharing my screen. Somebody online, everybody online can still hear me okay? Okay, perfect. So I was trying to set up a REML example and I'll keep working on that later. So would people prefer to see me actually try to type the code over or just work through an example where I actually, kind of did it ahead of time and we walked kind of through it?
Watch us struggle.
If that's what.
No, I like that.
And then can you share the updated example on GitHub when we're done?
Yeah, where I did it ahead of time or?
Yeah,
Or,
and the updated PowerPoint.
yeah, totally. I'll recommit the PowerPoint with the typo fixes. So there was one typo fix and then in one case I just confused myself, so I just added more text to myself. Okay, so I'll just rerun. Okay, so this is zoomed in. So just to be clear, this is sort of less efficient than, let's see, so you can do.
Wait, are we doing it or are you doing it?
Oh, well, do you want to do it? You want to just call stuff out?
Yeah.
Okay.
So yeah, just redo that tapply thing, pretty much copy it, and you can create a function called SE where it's just SE equals function x, SD over square root of length of x. And put that rather than the mean.
Totally. Index. CPE. Function. Back.
And then
SD back divided by square root. Swing back.
Yeah.
And then that's to get to the standard deviation of B in every year, and then from there, what do?
you have to turn it into the log normal SC.
Yeah, so, what did I call it before? Is it B sub T up above? Yeah, so I always like kind of doing intermediate stuff so I can inspect it later.
Uh-huh.
B of T, that's the CV. That's the CV in every year. And then the corresponding log normal index is,
Is that
is
the
this,
log of that
yeah, log,
squared plus 1?
yeah, log of CV squared plus 1. SD log BT equals the square root of the log CBT squared plus 1. Ever since Dell fixed my monitor, I've had weird keyboard issues. But, and so this makes sense that the log standard deviation is really close to the CV, which is sort of a property of the log normal, as long as the log SD is relatively low.
I forgot to log it, and that's why it wasn't.
Okay,
It works now.
okay. So this is the index that represents the kind of variation in the data, and given that variation in the data, how much you would expect the index to, how much error you expect in the index given the variation in the data that you have in hand. And it makes sense that you shouldn't have a better fit to your model than the variation you'd expect just from the data alone. Okay, and then on the other side, we can do, what's next? Anybody want to call it out?
Put in a data vector.
Just gonna keep it the same terminology on the other side. Normally I'd make the syntax match up more, but I'm making it. And then what's the other thing we have to do in here?
Then put it in the
In the likelihood.
likelihood component.
So,
So you add it on.
yeah, how, plus, how, T2, and then we want to take the square root of that whole thing, where how is the C++ function for power, so this is sigma squared, sigma m squared plus the standard deviation of the index squared, the sum of those, and then taking the square root of that. And hopefully, it doesn't balk at doing it this way. I guess, actually, I don't really need to do that, do I? Because I can just not commit it. Okay, so, so now I need to pass it and rerun it. Log SD log BT. And I'm calling it version 2, and I need to recompile and link it.
accuracy too.
Oh, yeah, yeah. So while it's compiling, double check that I didn't do anything I didn't remember. And so in this case now, the log sigma m that it's outputting is not really, it is just interpreted as the log of the additional variation after accounting for measurement error that's due to the, that's interpreted from the variation of the data. Chapar looks fine. I always just double check because I don't want to crash my computer if I overran something, so I kind of cautiously just double check that stuff looks like it's working well. That's working. So if we run it, it makes sense that we've now added log sigma m is now the additional variance on top of some other variance that we're forcing into the model. And so it makes sense that log sigma m is still going to 0. But the benefit of doing it this way is that we can plot, we can look at the fits of the model and yeah, so let's just see if we can. So if we look at the fits of the model, now at least it's not fitting the data, it's not fitting the index more tightly than we would expect given the variation that's in the data. So I think that this fit is an improvement, but we still have this problem of a parameter being in a bound. And so maybe as a class, we can finish up by just walking through, kind of coalescing what we learned about the map argument to see how we would turn off. Let's say we are willing to accept this hypothesis that the model is estimating, where it says basically that there's no additional variance besides the variance in the observation process that's due to the variation in the data. So we're okay with the model estimating that the additional variance log sigma m has gone to, the sigma m additional variance is not a 0. And instead of changing the model further, we just decide to fix that parameter at 0, so that we don't have a parameter hitting a bound. How would we do that using the map argument?
Yep. Yeah, set it to NA.
Yeah, so we make this empty list of map. I mean, this is the way I'm used to doing it. There's a bunch of ways you can build it, but I just make an empty list and then I start loading in stuff that I want to turn off. And it has to have the same spelling as the name of the parameter in the model. That's how it knows that it's the same parameter. So like I started typing in capital S and needed to make sure that it didn't do that. And if we want to turn off log sigma m, we just say factor NA, and that means that when I pass that map, it'll just leave that parameter at its start value. And what else do we probably want to do in this model?
Change the start value.
Change the start value. So parameters.
You could also use map to fix the log sigma m at some other value, right? If you wanted
Totally.
to.
Yeah, exactly. I'm kind of doing it this way, kind of in the theory that the model is trying to estimate it to 0, and we're putting in some other variants, and so we're just sort of willing to accept that it thinks that's the best fit. In reality, like if this was a stock assessment, we'd probably want to have some sensitivity analysis to different values of it or something. And so we want to start it out at some really low value. So like 1/10 trillion, whatever that is.
I think you got put in the E.
Yeah, and then we'll just recompile and rerun it. expect will happen when we rerun it this way?
We should sort of get back to the model we had before, right?
So it should, you know, all of the predictions of biomass should be the same as the model up here because we're just fixing it at the kind of zero where that was where it was being estimated.
But the SICs would be different.
What's that?
But the error off those estimates would be different.
Well, I think because it's going to zero already and we're just fixing it at zero, it probably won't really affect the predictions of error, but we can check that. And then I also predict that, you know, it'll have one less parameter, but it'll have essentially the same fit. So the AIC will be improved. So if any reviewer asks us why we fixed it, we could just say, well, we wanted to improve the AIC. And, you know, all of the standard errors, because we're eliminating the parameter that has a weird standard error, it'll just, all the standard errors will look better. And if we compare that with the original, opt SD versus opt reduced SD, yeah, those hypotheses both come out. You know, it's the exact same model, you know, to the 8th decimal place. So that's all I wanted to cover today. So the point is to reiterate what map does, how you can turn off parameters, reiterate how you can have a single C++ file that can do multiple models, but that differ in how you're using the map. Yeah. Okay. So you should have all the skills that are necessary to do the homework. Caitlin had asked a clarifying question about the homework about, well, there's 4 models listed in the homework. The simulation design is where you do 100 simulation replicates. You know, you simulate 100 data sets, and each data set you fit with 4 different models. So it's not like a 4x4 cross or like a factorial experiment or anything. It's just 100 simulated data sets, each fit with a 4 different models. It's only one dimension to the design.
1x4 instead of 4x4.
Exactly. Yeah.
Can I ask about the C++ code?
Yeah.
The most recent one. Right. Sorry, I just wanted to see it. I think I coded up different and got different results, but I think my predictions look the same as the ones you did, or when you plotted them.
Yeah, and let's see. So, and I can just plot it again, just to. So, well, yeah. So that's the fits with the. And is that kind of what you're saying?
Yeah, it's like exactly the same. Just interesting.
And you just calculated the CV instead of converting it to the log standard deviation or something. Is that what you're saying?
No, I did try to convert it at the end. I think my the uncertainty around my estimates is bigger.
But you can see that this is kind of working like a Kalman filter. So it's like pulling, you know, this observation and this observation are the blue, and it's pulling the estimated state, and the red is being pulled towards the adjacent observations. So like this red is closer to the high value, the blue, the year before. You know, so it's kind of smoothing out the extremes. I don't know, the intuition should be similar to the Kalman filter we were looking at before. So, okay, that's all I wanted to cover today. We're a little bit early. Any questions online before we finish up? Okay, well, thanks, okay, Grant.
Can you go back to your CPP file for the Gompers? For
The modified one?
Yeah. Oh, okay, cool.
Yeah, what were you checking for?
No, when I originally saw it, I didn't see the POW, comma 0.5.
Totally, yeah, exactly. So you were worried that I was summing the variances and then putting that in where it would interpret that as the standard deviation. Yeah, and so I needed to make sure. You know, if I was writing this out from, you know, as a real model that I'd use again, I would try to be generous to myself of the future and define this as something that I save that's called like standard deviation, so just block the code up into smaller pieces and make it easier to read in the future. Okay, well, thanks. So yeah, so I won't see you on Tuesday. Jay will do the lecture, but I'll be back on Thursday.